So welcome you to today's lecture. So last time we started with the elements of statistical inference problems. I gave you introduction about what do the statistical inference problems mean. Then we talked about what is a parameter, a basic goal in statistical inference problems. Then I gave an example of a statistical inference problem. Then we talked a little bit about how to draw a sample, which is a true representative of the population. Then we gave a formulation of the statistical inference problem. Then I introduced the notion of sample statistic, which is a function of random sample, and it does not involve any unknown parameter. Then I gave examples of some common statistics. Then I talked about sampling distributions, which is nothing but a probability distribution of any sample statistic. Then we talked about some popular standard sampling distributions like normal distribution, the gamma distribution, the exponential distribution, the central chi-square distribution, the student T distribution, that goes F distribution. And then I started doing some results on sampling distributions. Then the first result which I did was about the sample mean and sample variance from any arbitrary population based on a random sample. So if you have a sample mean based on a random sample, its expected value would always be same as mu. Its variance would be same as sigma squared by n. Expected value of sample variance, which is with a factor 1 upon n minus 1, would always be sigma squared. And variance of Sn square would be 1 upon n mu 4 minus n minus 3 n minus 1 sigma 4. So you can derive these results in a straightforward manner. Then I did a result that if x is a normal mu sigma square, then you know that if I standardize x, I can get a normal 0, 1. So that is what x minus mu by sigma would be normal 0, 1. And z square, which is x minus mu by sigma whole square, would be chi-square or more. So these are the standard results which you know from your BSc or the first course in probability and statistics. Now let's do some more results dealing with the sampling distributions. So the first result which we do today is about, suppose I have independent random variables x1, x2, xn, and xi has a normal distribution with mean mu I and variance sigma I square. Then for any real constants y1, y2, yn, so my xi's are normal mu I sigma I square, then for any real constant, I consider a linear combination of xi's, which is summation ai xi, should be again normal, which is its mean would be summation ai mu I, and variance would be summation ai square sigma I square. Now, you know how to prove it. It can be proved in a straightforward manner using the MGF. And this is a very standard result from your bachelor's. In particular, if x1, x2, xn are IID normal mu sigma square, or in other words, if x1, x2, xn is a random sample, then that means all of them have to be identically distributed. So same mean, mu, and same variance about sigma square. So if x1, x2, xn are IID normal mu sigma square, then if I take ai to be 1 upon n, my y becomes x bar. So my x bar would be same as normal. Each mu I is mu, and ai is 1 upon n. So 1 upon n summation mu n times, so n mu divided by n, that becomes mu. What will be summation ai square sigma square? 1 upon n square into sigma square, because all sigma i's are same. So 1 upon n square comes outside, and sigma square gets added n times, so n sigma square, it becomes sigma square. Not only that, if that is the case, then I know that if I standardize this, which is root n x bar n minus mu by sigma, would have a normal 1 distribution. Then let us do the next theorem, which is again for a sample from a normal distribution. Suppose I have a random sample from a normal population having mean mu and standard deviation sigma, which is 0 to infinity. So mean and variance both are finite. Then if I define x bar to be the sample mean and s square to be the sample variance with the factor as 1 upon n minus 1, then I know that x bar would have a normal mu and variance sigma square by n. I also know that sample mean and sample variance are independent if you're sampling from a normal distribution. So x bar and s square are independently distributed. Not only that, n minus 1 s square by sigma square would have a chi-square on n minus 1 degrees of freedom. And root n x bar minus mu upon Sn would have a t distribution from with n minus 1 degrees of freedom. So this all is your first course, which we have done at your bachelor's level. Those who have done BSc, they might have done this in BSc. Those who have done MSO 201, they would have done this result, MSO 201. So these are the useful results which I may be requiring in the later part of the course. Now let's do this distribution. Let Z is normal 0, 1. Let Z is normal 0, 1, and Y is chi-square mu, and Z and Y are independently distributed. Then if I define T nu to be Z on square root of Y by nu, so that is normal 0, 1. Basically, this quantity is nothing but normal 0, 1, which is Z, divided by square root of Y is chi-square on nu, and divided by nu. So this would have a T with n new degrees of freedom, provided these two random variables are independent. So Z is normal 0, 1, Y is chi-square on nu, and Z and Y are independent. Then if I take their ratio with Y divided by degrees of freedom, it would have a T with new degrees of freedom. So this is a very nice representation of a T distribution. So most of the time, I don't remember the PDF of a T distribution with new degrees of freedom. But what I remember is this representation, that a T distribution can always be written as a ratio of normal 0, 1 and square root of I-square divided by its degrees of freedom. Now, similar kind of a representation I have for F distribution, and which is what is given in the next theorem. For positive integers nu1 and nu2, let y1 is chi-square on nu1 and y2 is chi-square on nu2, and they are independent. Then if I define the ratio of chi-square nu1 divided by degrees of freedom, which is y1 upon nu1, and take the ratio of this with y2 upon nu2, which is chi-square nu2 by nu2, this would have a F distribution with nu1, nu2 degree. So in other words, your F distribution is nothing but chi-square nu1 by nu1 divided by chi-square nu2, and I require that they are independent. These all results you have done at your bachelor's level or the first course in probability and statistics. Now let's do a result about the reproductive property of a gamma distribution. So this is called the reproductive property. Reproductive in the sense that means if you add gamma random variable to gamma random variable, you again get a gamma random variable, provided the random variables are independent. So for positive real numbers theta, alpha 1, alpha 2, alpha k, let x1, x2, xk be independent random variables such that xi has gamma theta, that means my theta is same, and alpha is are changing. So my scale parameter same, which is theta, and my alphas are 10. Then if I consider summation xi, it would have a gamma with the same scale parameter theta and the same parameters getting added. Again, one can prove this easily by the movement generating function approach. In particular, if x1, x2, xk are independently distributed as chi-square on nu I, chi-square on nu I means you have a gamma with theta as 2 and alpha as nu I. Then their sum would be again chi-square, gamma, basically, with theta as 2. And you know that gamma with theta is equal to 2 is chi-square. And your nu I getting added. Okay, because it will be gamma nu I by 2. So this will be gamma summation nu I by 2, which is same as chi-square. So your chi-square and gamma have reproductive property. Let me introduce another distribution which is very commonly used, is called the beta distribution. For positive integers a and b, a random variable is said to follow a beta distribution with parameters a and b, written as x follows beta a and b, if its PDF is given by 1 upon beta ab, y to power a minus 1, 1 minus y to power b minus 1, 0 less than y less than 1, and 0 otherwise, where beta ab is the usual gamma function, and you know that this quantity, beta ab, is also same as 0 to 1, y to power a minus 1, b minus 1. So this is the beta distribution. Now, I have this result about relationship between gamma and beta distribution. What it says is if you have a positive real constants alpha 1 and alpha 2, and x1 has gamma theta alpha 1, x2 has gamma theta alpha 2, but theta is same, that means scale parameter is same, and they have a different shape parameters alpha 1 and alpha 2, and x1 and x2 are in. Then if I consider x1 divided by x1 plus x2, this would have a beta distribution with parameters as alpha 1 and alpha 2. Alpha 1 corresponds to x1, and alpha 2 corresponds to x2, which is x1 upon x1 plus x2 would have a beta. X equal to x1 plus x2, I already know that gamma has a reproductive property if theta is same, which is the case over here. So this will have a gamma theta with parameters as alpha 1 plus alpha 2. And not only that, the two would be independently distributed. So these are well-known results. Again, you might have done this at your bachelor's level, but it's good to refresh all those results. You can prove this using Jacobian method. It's straightforward to solve. This you can prove using the reproductive property of gamma. You can prove using MGF. This you can find again using the Jacobian method. T nu as z upon this also you can use using Jacobian. Okay, now let's talk a little bit about the order statistics. So let have a random vector. Suppose I have a random vector x, which is x1, x2, xn. And suppose its joint PDF is f of x. That means x1, x2 need not be even independent. Forget about this being a random sample. x1, x2, xn need not be even independent. So they have a joint PDF, f of x1, x2, xn. And I'm assuming that they have a Lebesgue PDF. Whenever I say that the random variable or the random vector has a Lebesgue PDF, what it means is it is absolutely continuous random. Right? So that means density exists. So it is a continuous random variable. So let x1, x2, xn be the corresponding order statistics. What does that mean? That means x round bracket r is the RS smallest of x1 to xn. I define a set of all permutations of 1 to n. Sn is beta 1, beta 2, beta n, such that beta 1, beta 2, beta n is a permutation of 1 to n. So I consider all the permutations of 1 to n, and they form the set Sn. So for example, Sn would have how many elements? It would have factorial n elements because there are factorial n permutations of 1 to n. But to see an example, you can see what would be my S3. It is a set of all permutations of 1, 2, 3. So all permutations of 1, 2, 3. 1, 2, 3. 1, 3, 2. Then 2, 1, 3. Then 2, 3, 3, 1, 2, 3, 2, 1. So these are a set of all permutations of 1, 2, 3. So similarly, I can define Sn to be the set of all permutations of the first n natural numbers. So it will have a factorial n elements. Then if I have to consider a joint PDF of x1, x2, xn, what do I have to do? I have to sum the joint PDF of y1, y2, joint PDF of x1, x2, xn with this y1, y2, yn replaced by all the permutations. You keep on permuting y1, y2, yn. So there'll be factorial n sums, and you can get this PDF. For example, in the case of n is equal to 3, as I said before, what will be my joint PDF of y1? Be my joint PDF of x1, x2, x3. If I have a random sample, it would be, I can write down this in terms of a joint PDF of x1, x2, x3. So it will be f of y1, y2, y3 plus f of y1, y3, y2 plus f of y2, y1, y3 plus f of y2, y3, y1 plus f of y3, y1, y2 plus f of y3, y2, and y1. The only thing is because they are order statistics, they should be restricted to this restriction that minus infinity less than y, less than infinity. Now the proof of this, you must have done it. If you have not done it, still it is straightforward. What you do is you look at joint PDF, joint distribution function of x1, x2, x3, that is order statistics. And then you sum over all possible values of x1, x2, x3. And you can get, I would leave eyes to you. Some of you may have already done it at your bachelor's level or in the first course, but you can take this as a. Now let's do a particular cases of this result. So suppose I have x1, x2, xn be independent. Now this is a general result of above theorem. Here xi's may not be independent. If they are independent, this joint PDF would be same as the product of individuals. So let x1, x2, xn be independent random variables with xi having the PDF of fi. Then the joint PDF of x1, x2, xn would be summation beta belonging to s, which comes from here. And what would be the joint PDF of this? It would be the product of marginals, which is product I is equal to 1 to n of fi of y beta I. So this result is just a particular case of this result for the situations where x1, x2, xn are independent. So this is. Now the next result is further particular of the above result. Now suppose you have a random sum. That means the random variables x1, x2, xn are not only independent, but they all have a same PDF, and suppose that PDF is f. And suppose the common distribution function is capital. Since this is a random sample, so they are IID. They are IID, they will have a same distribution function. I'm denoting that by capital F. They will have a same PDF, which I'm denoting by small f. Then the joint PDF of x1, x2, xn is factorial n times product of f of y minus infinity less than y1 less than y2. This follows from here because let us look at this inside sum, inside product. Inside product is each fi is same f. So inside product is f of y by beta 1, y beta 2, f of y beta n. F is same. But this y beta 1, y beta 2, y beta n, if you look at, they together form the set 1 to n, because that is a permutation of 1 to n, beta 1, beta 2, beta n. So this, in a sense, product, each of the product would be nothing but, because this I is same, f of y1, f of y2, f of yn. I can always rearrange them, right? Because typically this, in this situation, I will get here product I is equal to 1 to n, f, because each fi is same, y beta I. It is basically f of y beta 1, f of y beta 2, goes on f of y beta n. Now, note that this f is same in each of the product. And this y beta 1, y beta 2, y beta n together form y1, y2, yn. So y1 is a possibility would be sitting somewhere in the middle, y2 somewhere else, but together they form what? y1, y2, yn. So this is would be same as f of y1, f of y2, f of yn, because each fi is the same. So that means each of these product would be f of y1, y2, yn. It does not depend on whatever beta may be. And how many betas are there? Factorial n. So that is why factorial n. And this quantity has been summed factorial n times, which is product I is equal to 1 to f of 5. Now, for the random sample case, you might have done at your last course, the marginal PDF of the RS order statistic is XR. I know PDF is factorial n, factorial r minus 1, factorial n minus r, fy to power 5 to power r minus 1, 1 minus fy to power n minus r, fy, y between minus infinity to infinity. So the joint PDF of xr and xs, where r is less than s, r less than s means xr is smaller than xs. So I'm in the first argument, I'm taking a smaller order system. In the second argument, I'm taking s bigger than s. So that means that is a larger order. So joint PDF of RS and SS order statistic, where r is less than s, is given by factorial n, factorial r minus, factorial s r minus, factorial n minus s. Fx to power r minus 1, fy minus fx to power s minus r minus 1 minus fy, fx, fy, minus infinity less than x. Note that if you didn't have a random sample, that means if xi's were not identically distributed, this expression would be slightly complicated. It would be in sum of betas with fi's coming over here. But in the case of random sample, the PDF of XR and XS are available in a very nice compact. So this was about joint PDF of RS and SS order statistic. Now then there are other results which are of use. One such result comes from your central limit theorem. So let me just write down those over here. So the one result which is again very useful is called weak law of large numbers. Or a stronger form, which is called strong law of Again, this is a result from your first course. What it says, let x1, x2 then be a random sample from a population having finite mean. Mu is the population. Then bar, which is basically sample mean, then x bar. So erase this. Then x bar, which is a sample mean, x bar is happening. Let me just. Okay. Then x bar I'm not able to. You have to get used to this. Okay. Then bar converges in probability to mu. What does that mean? Means every epsilon greater than 0 limit and going to infinity of probability that mod of x bar minus mu is greater than or equal to epsilon would be 0. This is a result which you already know. In fact, one can assert much stronger statement or much stronger result that probability of limit and going to infinity is same as mu. So probability that x bar would converge to mu, that is 1. So this result is called weak law of large numbers, WLLN, weak law of large numbers. This is called strong law of large numbers, SLLN. And everybody knows that strong law of large numbers is much stronger than weak law of large numbers. This implies this. So this is a well-known result from your probability theory. Again, I will not prove this because this you might have already done in your earlier course.
Sir, what is the difference between two?
The difference between the two is that this doesn't mean that limit x bar would be same as mu. It only says that for every epsilon greater than 0, if you take any epsilon fixed greater than 0, then probability that mod of x bar minus mu greater than or equal to epsilon, if this probability you consider, that probability would go to 0. What it says is probability that limit of x bar would be mu would be 1. So one can show that this implies this. If this holds, probability limit x bar is equal to mu is 1. then this probability would be 0. One can show that. Converse may not always hold, right? One can show that. And that's the difference between the weak law of large numbers and strong law of large numbers. That strong law of large numbers asserts something which is a much stronger result. That means it asserts this, which implies this, right? So, in fact, if one has to look at a result, one should consider only this result because this is much stronger than this result, as this implies this. All right, any doubt you have?
No, sir.
Yeah, so one can, so that this you may be doing in a probability theory course, or you might have already done in your probability theory course, right? Strong law of large number. Convergence almost surely implies convergence in probability, right? So
Actually, sir, in this course, we have this kind of things.
you did not do this convergence before?
No, sir, SLLN hasn't done by me.
Okay, so in that case, I would say that remember weak law of large numbers, right? That is what I'll be using most often. WLLN is done, right? That is done at bachelor's.
Yes, yes.
Okay, so in that case, just remember WLLN. And if I would be using SLLN at any of the occasions, I would again revisit it and I'll explain you what does it mean, right? That was supposed to be a part of your probability theory course. Now I do a famous result which is called the central limit theorem. What does central limit theorem says? And actually, central limit theorem is one of the most important results in statistics, right? Half of the statistics, not half of them, is a substantial part of the subject relies on this central limit theorem or its various versions in the multivariate case and so on. So what it says is, suppose I have a random sample, x1 next to xn, be a random sample. Population with mean mu and variance sigma square, which I'm assuming is fine. Right. Then root n, I normalize this sample mean, root n x bar minus mu sigma will converge in distribution to z, which is normal 0, 1. So it is irrespective of the population you're sampling from. If I normalize the sample mean by subtracting the mean mu, I know that variance of x bar is sigma square by n. If I consider the standard deviation of x bar is sigma by root n. So that is how it comes. It comes, that can be approximated by normal 0, 1. What does it mean? That means if I consider in limit n going to infinity of probability that root n bar minus mu sigma is less than or equal to z, that would be same as minus infinity to z 1 by root 2 pi e to power minus t square by 2. Because normal 0, 1, this is what the density is. And you're talking about probability that this quantity is less than or equal to z. That means, and this result says this can be approximated by the normal probability. So this is what the central limit theorem says. This is a very important result and you'll be using it at various occasions. So it's nice to remember it. And again, proving it is not difficult. You can prove this using characteristic function or the moment energy function. The proof you might have done at your bachelor's level. Let me again go back to my earlier slides. So I've done central limit. So this was all about the sampling distributions. Now let me discuss a little bit about parametric statistical inference. I have in general talked about statistical inference problems. Let me now talk about parametric statistical inference problems. Now here the random variable x has a PMF or probability density function f, which depends on certain parameter theta. But your PDF has a known functional form. That means the functional form of the PDF is known. For example, in the normal case, I know the functional form as 1 upon root 2 pi e to power minus x minus mu whole square by sigma square. In the case of exponential, I know the functional form. It is 1 by theta e to power minus x by theta. So when I talk about parametric statistical inference, what it means is my density has a known functional form, except that it may have some unknown parameter, which I'm denoting by theta. So that is what is being said over here. Here the random variable x, which describes a population, has a PMF or PDF f dot given theta, is a known functional form, except perhaps for the unknown parameter theta that may be vector valued. For example, if I'm dealing with an inference problem involving normal distribution with mean mu and variance 1, that is a parametric statistical inference problem because the form of the density is 1 upon root 2 pi e to power minus half x minus mu whole square. So your functional form is known, mu may be unknown. That's okay. Here, theta is the set of all possible values of unknown parameters theta. So what is a basic parametric statistical inference problem? Based on the suitable selected sample, to decide which member of the family can represent the PMF or PDF of X. So I try to find out some information about the PDF of. Here, functional form of F is unknown, the only unknown, a functional form of F is known, so the only unknown quantity is theta. So basically, problem boils down to making certain conclusions about this parameter theta. Then we have a non-parametric statistical inference problem. In non-parametric statistical inference problem, the functional form of the density may not be known. What may be known at the best is that possibly your distribution is continuous or discrete. Apart from that, you may not have much information. At least the functional form will not be known. So in the non-parametric statistical inference problems, we do not know the functional form of the distribution function f or the PDF f, except perhaps that f possesses certain property. Example, f is continuous. The failure rate, which is defined by fx upon 1 minus fx, is increasing, or something like that. That I would at the best know some property of the PDF. In the parametric statistical problems, let the joint PMF PDF of observable sample x1, x2, xn is denoted by g of x1, x2, xn given here. So the functional form of g is known. Theta may be unknown. I can talk about the likelihood function of the observed sample, which you have already encountered in your last course when you were deriving the maximum likelihood estimator, or when you were deriving the name and Pearson lamp. So here let x1, x2, xn be the observed sample. So that means after the experiment has been conducted, I observe the sample as x1, x2, xn. In other words, x1, x2, xn, this small x1, x2, xn, is a realization of the random variables x1, x2, xn. Note that here, the observed values are denoted by small xi, and random variables are denoted by capital Xi. So after the experiment has been conducted, suppose x1, x2, xn are the observed values of the sample, which are random values. Then the joint PMF PDF of observable x1, x2, xn at the point x1, x2, xn as a function of unknown parameter theta is called the likelihood function of the observed sample x1, x2, x. So what is your likelihood function? Likelihood function is nothing but joint PDF of sample when it is considered as a parameter, as a function of the parameter theta. So I consider joint PDF of x1, x2, xn as a parameter of theta. I am denoting that by L of theta x1, xn. I call this as a likelihood function. So if we have to define likelihood function in very simple terms, what it means is it is nothing but joint PDF as a function of theta for the observed values of the sample. Observed values of the sample for x1, x2. Note that for observed values of x1, x2, xn, its likelihood function at the point theta may be interpreted as the likelihood of the observed sample having come from the PDF f dot theta. Because this gives you the probability of observing x1, x2, xn, because it is a joint PDF. So in certain sense, it is a probability of observing the given sample which you have observed when theta is the true parameter. Or in other words, this denotes the probability that your sample came from a population with PDF theta. This is, in a certain sense, denotes the probability that observed sample xn comes from a population having PDF or PMF f theta. And that is right. You try to look at for which theta this probability is maximum, and you take that as a maximum likelihood estimator to estimate theta. Because for that theta corresponds to the probability says that the observed sample x1, x2, xn is coming from the population f theta hat is maximum. I can talk about parametric point and interval estimation. So in this course, I'll be mainly dealing with parametric inference problems and mainly the parametric estimation and parametric hypothesis testing problems. So suppose x is a random variable describing some characteristic of units in the target population. F dot theta is the PDF or PMF of x. I know the functional form of f, and possibly theta is unknown. Theta is the parameter space. This is a set of all possible values of unknown parameter theta. So what I have is x1, x2, xn, which is observable sample. Small x1, x2, xn is observed values of x1, x2, xn. So these are the realization of x1, x2, xn after the experiment has been conducted. Goal is, on the basis of observed sample x1, x2, xn, to estimate the value of the unknown parameter theta or the value of some function, say c theta of theta. So I'm either interested in estimation of theta or its function c of theta. In the point estimation problem, I'm interested in a certain point so I want a precise estimate of psi theta. In the parametric point estimation, a statistic t is desired that can be used to estimate the value of psi theta. So that gives me the exact value of the psi theta, even if psi theta is vector value. Note that tx1, x2, xn is a random variable and is called a point estimator of psi theta. So tx1, x2, xn as a function of random variables x1, x2, xn is called an estimator or a point estimator of psi theta. If x1, x2, xn is the observed sample after experimentation of sampling, then the t evaluated at the observed sample x1, x2, xn is taken as an estimate of the unknown quantity parameter or unknown parameter psi theta. And tx1, x2 is called an estimate of psi theta. So there's very subtle difference between an estimator and estimate. Estimator is always a function of random variables, x1, x2, xn, which we have not observed, tx1, x2. Whereas estimate is after experimentation has been done or the sampling is being done, the value of the estimator calculated at the observed values of the sample is called an estimate. Now, in the parametric interval estimation problems, I'm not interested in a point which estimates theta or psi theta. Rather, I'm interested in an interval which depends on two statistics, t1, x1, x2, xn, and t2, x2, xn. So I'm interested in an interval which contains the unknown parameter with certain high probability. Two statistics here, two statistics t1 and t2, with t1 less than t2, are observed, are desired, so that the interval t1 to t2 can be used to provide an interval estimate of psi theta. Now, normally one would expect that the interval t1, t2 contains psi theta with high probability. Now, note that one can always say that if your theta is real value, one can always take t1 to be minus infinity and t1 to be plus infinity. The probability that your theta lies in that interval is 1. But in this case, although the probability of confidence that interval contains theta is high, is the best you can have, which is 1. But this interval does not provide me any information, because I already know that theta is a real. So there is always a trade-off between the length of the interval and the confidence you want to have in that interval. So what you do is, by sacrificing a little bit on the confidence, you can get a reasonable confidence interval or a confidence interval of a reasonable length. And that is the reason why normally you look for a 95% confidence interval or a 90% confidence interval or a 99% confidence. For the 99% confidence interval, although the fall in confidence is only 0.01 from 1, but you can get the length of confidence interval to be finite. Certainly 95% confidence interval in comparison to 99% confidence interval, confidence is less. But at the same time, for the 95% confidence interval, generally you will get an interval whose length is smaller. Now, if its length is smaller, what does that say? It says that theta, I have information that theta lies in some smaller interval with very high probability. So if I can claim that theta lies in a smaller interval, that means I have more information about theta. So for example, I can say that theta lies between 1 to 2 is 20.95. May have a statement that theta lies between 2. Yes. Now, if I want to increase this confidence interval, but normally that would come at the cost of this larger interval. So that would be 0.5 to 3. And that would normally come out to be 0.9. So you can see the trade-off here. Confidence is less, but I can estimate theta more precisely. Because here theta says that theta only lies between 1 and 2. Here confidence is more, but then theta says that theta is in a larger interval. So here I have a lesser information about theta. Here I have more information about theta because I'm saying that theta is concentrated in only 1 to 2. Here I'm saying theta is considered in a much larger interval than this. In fact, the other extreme would be probability that theta lies between minus infinity to infinity. So here I have boosted my confidence to 100%, but I do not get any information from my confidence because it says theta lies between minus infinity to infinity. So there is always a trade-off between the confidence level and the length of the confidence interval. In the parametric hypothesis testing problems, I'm interested in testing certain statement about the parameter size. So it is desired to test a given hypothesis H0 about the unknown parameter psi theta based on the observed sample x1, x2, xn. So for this purpose, I've written down paper, for this purpose, generally a rejection region C, which depends on x1, x2, xn, is identified so that if the observed sample x1, x2, xn falls in the region C, the decision of rejection of the hypothesis H0 is taken. So basically here problem is that of finding a critical region or the region of rejection of H0, which you did in your bachelor's. Now note that the confidence interval T1 to T2 is random quantity, and if x1, x2, xn is observed sample, then T1x, T2x is taken as an interval estimate of psi theta. So I can get precisely this interval only after the experimentation. That means after I have observed this x. Once I do that after experimentation, I evaluate this, that is called an interval estimate. So that's a difference between interval estimator and interval estimate. Now, when the sample size n is large, typically the sample x1, x2, xn may contain some redundant information that may not be of direct significance to making inferences about the unknown parameter theta. Now, for providing efficient statistical inferential procedures, that is why it is important that I should get rid of all this redundant information. So that means I try to squeeze this x1, x2, xn through some statistic. Or I try to summarize the information contained in x1, x2, xn through some statistic. Now, this leads to the notion of sufficiency or a sufficient statistic. And that is what we'll discuss in our next lecture. So this was all about module 1. So this is end of 2. So in the next lecture, I'll start with sufficient statistic. If any one of you have any questions, feel free to ask. Those who don't have any question, if they want, they can leave. I would stay back for any questions if any one of you have. So that's all for today. Yes.
Sir,
Yeah.
sir, can you please explain once more what does Lebesgue PDF mean?
So Lebesgue PDF basically it means is it's a major theoretic term. So whenever I use the term Lebesgue PDF, what it means is your random variable is continuous. So when I say that x is a random variable with Lebesgue PDF, let us say x is a random variable with distribution function f and Lebesgue PDF f, what it means is my distribution function fx can be written in terms of an integral, usual integral x, ft, dt. And which is a definition of an absolutely continuous random variable, right? I say that my random variable is absolutely continuous if there exists a non-negative function small f such that this holds. So in this course, whenever I'm saying that my random variable has a Lebesgue PDF, what it means is my random variable is absolutely continuous with my distribution function fx, which is probability x less than or equal to x, is given by what it means. Similar thing I can be said in the case of multivariate observations. In that case, x would be a random vector, and probability x1 less than or equal to x1, x2 less than or equal to x2, probability xn less than or equal to xn. same as minus infinity to x. Minus infinity to x. F T1, T2, T. So actually this Lebesgue PDF is a very common term. It is used because the probability theory is a part of a measure theory. And when you do a course on a measure theory, you say that normally you talk about the density exists with respect to some measure. So when I say it is a Lebesgue PDF, it means my density exists with respect to a Lebesgue measure. But that is in the context of a measure theory course. For the purpose of this course, whenever I'm writing down Lebesgue PDF, you may assume that my random variable is continuous, which basically means that distribution function f is given by minus infinity to x ft or its joint distribution function. If that is the case, minus infinity to x is given by minus infinity to x1, minus infinity to xn, f of t1. Have
Okay,
I been,
sir. Yes, sir. Thank you, sir. Thank you, sir.
yeah. If anyone has another question, yeah, feel free to ask it, and others may leave. So I'll be giving one homework problem today or sometime tomorrow on sampling distributions. Try to do those problems. So I still see Abhishek. Can you hear me? Abhishek.
Yes, sir. Yes, sir.
Okay. So I'm just
Sorry, sir. I forgot to leave. Actually,
I'm finishing the meeting.